In this video, we're going to talk about the concept of electric potential energy. So let's begin our discussion with a picture. Let's say we have two parallel plates. The first one, the one on top, is going to be positively charged. The second one is going to have a negative charge. Now we know that the electric field will extend from the positively charged plate and it's going to point towards the negatively charged plate. Now let's say we have a positive charge between these two plates. This positive charge will feel a force that will accelerate it in the same direction as the electric field, which in this case it's going to be the negative y direction. A negative charge will feel a force that will accelerate it in the opposite direction of the electric field. Now let's say this is point A and the charge is moving to point B. How can we determine the electric potential energy at each of these points? So let's say that point B is at a position YB above the negatively charged plate, and point A is at a position YA above the negatively charged plate. So here's what we can do to come up with a formula to calculate the electric potential energy. So we're going to start with this. The work done going from A to B is going to be equal to the negative change in potential energy. So potential energy, you could represent it as PE or capital U. You need to be able to distinguish gravitational potential energy from electric potential energy. Some textbooks will use U sub G to represent gravitational potential energy, which is mgh. Others will use UE to represent electric potential energy. And some will just use PE, so be careful with those differences. Let's use capital U in this video to represent electric potential energy. Now we know that the work is equal to the force times the displacement. And going from A to B, we have the change in potential energy. So final minus initial. The final potential energy will be at B, and the initial electric potential energy will be at A. Now the electric force is equal to the magnitude of the electric field times the charge. So we can replace F with E times Q. Now D represents the displacement. So as we move from A to B, the displacement is going to be the change in position. So it's YB minus YA. By the way, let's take this negative sign and let's move it to the other side. So I'm going to make this positive, make this negative. So the displacement is Y final minus Y initial, or YB minus YA. Now let's distribute negative EQ. So we're going to have negative EQ times YB, and here we have two negative signs, so it's going to be plus E times Q times YA. So UB is equal to negative EQ YB. Negative UA is equal to positive EQYA. If you multiply both of those by negative 1, you'll get that positive UA is equal to negative EQYA. So we can thus say that the potential energy, the electric potential energy, is going to be negative times the electric field times Q times Y. So this is the equation that can help you to calculate the electric potential energy. Notice how it's similar to the gravitational potential energy, which is equal to mgh. In both cases, the potential energy is dependent on the position from ground level. In this case, the negatively charged plate can be considered the ground level of this particular structure. Let's work on this problem. A 50 microcoulomb point charge moves from point A to point B as shown in the diagram below. The magnitude of the electric field is 2 times 10 to the 6 newtons per coulomb. Points A and B are 80 centimeters and 20 centimeters above the negatively charged plate respectively. Part A. Calculate the electric potential energy at points A and B. So we know that this positive charge is feeling an electric force that's going to accelerate it towards the negatively charged plate. And we know that B is 20 centimeters above the negatively charged plate, and A is 80 centimeters above it. So to calculate the electric potential energy at these points, we could use this formula. The electric potential energy is going to be negative times the electric field times the charge times the position above the negatively charged plate. So what's E? We have the magnitude of E is 2 times 10 to the 6. But notice the direction of E. E is going in the negative y direction. So for this formula to work, we need to plug in negative 2 times 10 to the 6 newtons per coulomb. And then we have the charge. So Q is positive 50 times 10 to the negative 6. And then we need to plug in the height. So let's calculate the potential at A first. So if we calculate the potential at A, we need to use the position at A. It's 80 centimeters, so that's going to be 0.80 meters. So the two negative signs will cancel, which will give us a positive answer. So the electric potential energy at point A is going to be 80 joules. Now let's calculate it at point B. So it's going to be negative times negative 2 times 10 to the 6, and then 50 times 10 to the negative 6, but this time times 0.20. So UA is going to be 20 joules. So that's how we can calculate the electric potential energy. This is supposed to be UB, my mistake. So that's how we can get the electric potential energy at those 2 points. Now what can we say about the change in electric potential energy as well as kinetic energy going from A to B? Is it positive or negative? And what about the work done on a positive charge going from A to B? Is that positive or negative? Well, the electric potential energy is decreasing as we move from A to B. We went from a value of 80 to 20. So the electric potential energy is decreasing, which means that the change in electric potential energy is negative. As the electric potential energy decreases, the kinetic energy will increase. As the electric force accelerates the positive charge towards the negatively charged plate, the speed of the charged particle is going to increase, so the kinetic energy is going to increase. And since work is equal to the change in the kinetic energy, if the change in kinetic energy is positive, the work done on the charged particle will be positive. Another way in which you can determine the sign of work is looking at the force and the displacement vectors. If these two vectors are in the same direction, the work done is positive. If they're opposite to each other, the work done is negative. If they're at right angles to each other, the work done is 0. The charged particle is moving in the negative y direction, so its displacement vector is downward. Since these two vectors are in the same direction, the work done is going to be positive. But now let's go ahead and calculate the work done in this example. So work is equal to the negative change in potential energy. So that's going to be the final potential energy minus the initial potential energy. The final, or UB, is 20. The initial is 80. So it's going to be negative 20 minus 80 is negative 60. So as we can see, the work done is positive 60 joules. So that's the answer for part B. So that's how we can calculate how much work is done going from point A to point B. Now let's move on to part C. What is the electric potential at points A and B? Before we answer that question, let's erase a few things and rewrite some of our values above. So with this information and everything else that we know, how can we determine the electric potential at points A and B? The electric potential is equal to the electric potential energy divided by charge. So make sure you understand that. The electric potential energy, I'm going to write EPE, that's capital U. V represents the electric potential. The electric potential energy is measured in units of joules. Electric potential is measured in volts. 1 volt is 1 joule of electric potential energy per 1 coulomb of charge. So electric potential measured in volts is the ratio of electric potential energy in joules per unit charge in coulombs. So if we wish to calculate the electric potential at point A, it's going to be the electric potential energy, which is 80 joules, divided by the charge. And the magnitude of the charge is 50 microcoulombs, or 50 times 10 to negative 6 coulombs. So this is a very large number. It's 1.6 million. So we can say 1.6 times 10 to the 6 volts, or just keep in mind 10 to the 6 is mega, so we could say 1.6 megavolts. You could also say 1600 kilovolts. Maybe that will be a better value to deal with here. Now let's calculate the electric potential at B. It's going to be 20 joules divided by the same charge. So that's 400,000 volts, which is 400 kilovolts. So that's how we can calculate the electric potential at each of these points if we know the charge and the electric potential energy. Now we can also confirm this answer. Another way in which we can calculate work is by using this formula. The work required to move a charged particle through a potential difference is equal to negative Q delta V. So Q is positive, it's 50 times 10 to the minus 6. And we're going from A to B. So going from A to B, the change in voltage as we go from 1600 kilovolts to 400 kilovolts, the change in voltage is negative 1200 kilovolts. It's final minus initial. 400 minus 1600 is negative 1200. So this is negative 1200 kilovolts, or negative 1200 times 10 to the 3 volts. And this will give you the same answer, positive 60 joules. So in all cases, we can see that the work done on this charge to move it from point A to point B is going to be positive. Now I'd like to take a minute to highlight the similarities between gravitational potential energy and electric potential energy. So let me just clear away a few things. So electric potential energy is dependent on the height. In this case, we'll call it y. Now, when we analyze an object that could fall under the influence of gravity, the gravitational potential energy is also dependent on the height. The gravitational potential energy is equal to the mass times the gravitational acceleration times the height. The electric potential energy is equal to the charge times the electric field times the height. So note the similarities between these two equations. These are both forms of potential energy. So here we have charge, here we have mass. Here we have the electric field, and here we have the gravitational field, or the gravitational acceleration. And then both of them are dependent on the height. So if you can remember this equation, that will help you to remember this one as well. Number 2, a 70 microcoulomb charge is located at a point where the electric potential is 300 volts. What is the electric potential energy of this charged particle? We know that electric potential is equal to the electric potential energy divided by charge. But in part A, we want to calculate the electric potential energy. So rearranging that equation, or multiplying both sides by Q, we get that the electric potential energy is equal to the charge times the electric potential. So we have a 70 microcoulomb charge, and the electric potential is 300 volts. Keep in mind, 1 volt is equal to 1 joule per coulomb. So instead of writing 300 volts, we can write 300 joules per coulomb. So we can see that the unit coulombs will cancel, giving us the unit joules. So it's 70 times 10 to the negative 6 times 300. So the answer for part A, the electric potential energy will be 0.021 joules. Now let's use the same formula for part B. So it's going to be U is equal to QV, and this time we have a negative 60 microcoulomb charge. So since electric potential energy can be positive or negative, we're going to plug in negative 60 times 10 to the minus 6. And this time, the electric potential is 500 instead of 300. And so this is going to be negative 0.03 joules. So that is the electric potential energy of a negatively charged particle with an electric potential that's positive. If we had a negatively charged particle with a negative electric potential, the electric potential energy will be positive because the two negative signs will cancel. So for instance, let's say we have a negative 90 microcoulomb charge located at this point where the potential is negative 400. So using this formula, we're going to get a positive result. It's going to be negative 90 times 10 to the minus 6 times negative 400. And that's going to be positive 0.036 joules. So the electric potential energy could be positive or negative. Number 3, a 100 volt battery is connected to 2 oppositely charged parallel plates that are separated by a distance of 10 millimeters. Calculate the electric field. So here we have the direction of the electric field. We have the voltage of the battery, it's 100 volts, and we know the distance between the 2 plates. The formula that we need to calculate the electric field is this formula. It's equal to the change in voltage divided by the displacement. For those of you who want to keep it simple, you could say it's the voltage across the plates divided by the distance of the plates. But for those of you who want to be more technical, there is a negative sign involved. But let's keep it simple. We're just going to use V over D. The voltage is 100. The distance between the plates is 10 millimeters, which is, to convert that to meters, you need to divide by 1,000. There's 1,000 millimeters in 1 meter. So 10 divided by 1,000, this gives us 0.01 meters. So the electric field is 10,000 volts per meter. The electric field tells us how the electric potential changes over distance. So for every 1 meter that you move, the electric potential changes by 10,000 volts. Now if we want to get it in volts per millimeter, we could have done this. We could have done 100 volts divided by 10 millimeters. And we could say that the electric field is 100 divided by 10 is 10. So it's 10 volts per millimeter. So if we move by a distance of 1 millimeter in this between these parallel plates, the electric potential will change by 10 volts. So let's say at this plate is 100 volts, at this plate is 0 volts. Let me put these numbers over here. So let's put 0 over here and 100 over here. And let's say this is the distance between the plates. So here it's at 0 and here it's at 10 millimeters. If we were to move 1 millimeter above the negatively charged plate, the electric field will change by 10 volts. If we move another millimeter, it's going to increase by 10, so now it's going to be 20. In part B, we want to calculate the electric potential at a point 7 millimeters above the negatively charged plate. So 7 will be maybe somewhere over here. So this is going to be an electric potential of 70 volts. To get that answer, you could simply rearrange this formula. The electric potential, V, is going to be the electric field times the distance. So the electric field, using this one because we have the unit millimeters, is going to be 10 volts per millimeter. And then if we move a distance of 7 millimeters, these units will cancel. It will be 10 times 7, and that will give us an electric potential of 70 volts. So that's how you can calculate the electric potential at any point between the two parallel plates. It's simply the electric field times the distance. But you do need to pay attention to the units. You want to make sure that the units match if you're going to use that formula. Now let's talk about the formula above. For those of you who want to understand the negative sign and how it works, let's get rid of a few things. And we'll talk about how we can derive that formula. So let's say if we have a positive charge and it's moving from position A, where the potential is 70, to position B, where the potential is 20. So as we move from A to B, how is the potential changing? The final potential is 20. The initial potential is 70, so the change is negative 50. Now the displacement relative to the negatively charged plate is, what's D? The displacement is going to be negative 5 millimeters if we move from point A to point B, because we're going down the negative y-axis. If you take displacement as the final position minus the initial position, this is your final position 2 minus your initial position 7, so you get negative 5. So here we have negative 5 millimeters. So it's negative, and then 20 minus 50 is negative. So we have a change in potential of negative 50 and divided by negative 5. So these two will cancel. So we have positive 50 volts divided by negative 5. And so we're going to get negative 10 volts per millimeter. So what we have here, this is just the magnitude of the electric field. But in fact, it should be negative. The reason why it's negative is because the electric field is moving in the negative y direction. So that's the purpose of the sign. It tells you the direction of the electric field. But since we already know the direction, we really don't need to worry about the negative sign. We could say the electric field is simply the voltage across the plates divided by the distance between the plates. You could just use this to determine the direction, but if you know the signs of the plates, you can easily determine the direction of the electric field. It's always going to move from the positive plate toward the negative plate. But now you understand how to use this negative sign in that formula. Now let's talk about how to derive that formula. You can start with this equation. Work is equal to, this is the work done by an electric force, is equal to negative Q times the potential difference through which that charge is accelerated. Now work is equal to force times displacement. And the electric force acting on a charged particle in an electric field is equal to the electric field times the charge. F is equal to EQ. So to calculate the electric field, we need to divide both sides by QD. QD will cancel on the left, but only Q will cancel on the right. And so we're left with this equation. The electric field is equal to negative times the voltage divided by the displacement. So that's how you can derive that formula. Now let's move on to part C. What is the electric potential energy of a 400 microcoulomb charge placed 7 millimeters above the negatively charged plate? So we want to calculate the electric potential energy at point A. So we have a charge at point A, but we also have the magnitude of that charge. To calculate the electric potential energy is simply the charge times the electric potential. So we have a 400 microcoulomb charge, and at 7 millimeters above the negatively charged plate, the electric potential is 70 volts. Let's convert microcoulombs to coulombs. So this should be 400 times 10 to negative 6 coulombs. And then we'll multiply that by 70 volts. So the electric potential energy is going to be positive 0.028 joules. So that's how we can use that formula to calculate the electric potential energy. Now let's confirm our answer with the other formula that we've used for this situation. So if you recall, the electric potential energy is also equal to negative times the charge times the electric field times the height above the negative plate for a positive charge that falls towards the negative plate. And let's put it over here. So Q is positive 400 times 10 to negative 6. The electric field, and I just got rid of it, but it was 100 volts divided by 0.01 meters, so it was 10,000 volts per meter. Now the electric field is going in the negative y direction, so we need to apply that negative sign to get this right. And the height above the negatively charged plate, point A is 7 millimeters above it. Now this is in meters, so we want this to be in meters as well. 7 millimeters, if you divide that by 1,000, that's going to be 0.007 meters. If we use the electric field in volts per millimeter, then we could use millimeters here. But you want to make sure that these units, they match. So it's negative 400 times 10 to negative 6 times negative 10,000 times 0.007. And this gives you the same answer, positive 0.028 joules. So both formulas work. So now you have two ways in which you can calculate the electric potential energy above some reference point. It's equal to the charge times the electric potential, and it's also equal to the charge times the electric field times the height with a negative sign. Number 4. A proton is released from rest in a uniform electric field with a magnitude of 500 volts per meter directed along the x-axis. The proton travels a distance of 0.4 meters in the direction of the electric field. Calculate the change in electric potential of the proton. Well, let's draw a picture. So we know that the electric field is directed along the positive x-axis. So it's going towards the right. And then let's draw a proton. So a proton is a subatomic particle of a positive charge. It's going to feel a force that will accelerate it in the same direction as the electric field. So that is towards the right. And we know it's moving to the right with a displacement of 0.4 meters. So that's the information that we have. Calculate the change in electric potential of the proton. How can we do this? Recall that the electric field is equal to the change in electric potential, or the negative change in electric potential, divided by the displacement. So if we multiply both sides of this equation by negative d, we'll get that the change in electric potential is equal to negative E times d. So let's use that formula. The electric field is 500 volts per meter. So that's the magnitude. Is it positive 500 volts per meter or negative 500 volts per meter? What would you say? In order to determine if it's positive or negative, we need to look at the direction of the electric field. It's directed along the positive x-axis. So that means that E is going to be positive 500 volts per meter. Now what about the displacement? We know the displacement is distance with direction. The 0.4 meters represents the magnitude of the displacement. What is the direction of this vector? The displacement vector is east, because the proton, it was released from rest and it's going to accelerate in the direction of the electric field, that is, along the positive x-axis. So therefore, the displacement is not going to be negative 0.4, but positive 0.4. If the proton was moving to the left, we would use a negative 0.4. So we can see that the unit meters will cancel, and we're going to get the change in electric potential in volts. So it's going to be negative 500 times 0.4. So the change in electric potential, let's say going from point A to point B, is negative 200 volts. So that's the answer to part A. Now, does this answer make sense? Should the change in electric potential be negative, or should it be positive? Let's see if we can make sense of the answer. But first, let's clear away a few things. What you need to understand is that the electric field will always travel from a region of high potential to a region of low potential. If we were to draw two parallel plates, we know that the electric field will always point away from the positively charged plate, and it's going to point towards the negatively charged plate. Let's say this is 0 volts, just picking an arbitrary number, and let's say this is 100. Notice that the electric field is moving from a high potential to a low potential. And when the proton accelerates in the direction of the electric field, which it usually does, it too will move from a high potential to a low potential. So as the proton moves from, let's say, point A to point B, the potential is decreasing. If the electric potential is decreasing, then the change in potential is going to be negative. And so we can see why we have this answer, negative 200. The negative sign makes sense. As the proton moves in the direction of the electric field, it's going to move from a high potential to a low potential. and so the change in electric potential should be negative. Now let's consider part B. Calculate the change in electric potential energy of the proton. So electric potential is measured in volts, but electric potential energy is measured in joules. So how can we calculate the change in electric potential energy? Now recall earlier we said that electric potential energy is equal to the charge times the electric potential. Now we want the change in electric potential energy. So that's going to be the charge times the change in electric potential. So what is the charge of a proton? A proton carries a positive charge, and it's 1.602 times 10 to the negative 19 coulombs. These are just one of those numbers that you need to commit to memory. Now we have the change in voltage, or I would say the change in electric potential, which is voltage. That's negative 200 volts. Or we could replace the unit volts with joules per coulomb, so that we can cross out the unit coulombs and get the unit joules. So the change in electric potential energy is negative 3.2 times 10 to the negative 17 joules. So that's the answer for part B. As the proton moves from point A to point B, we know that the speed is going to increase. Therefore, the kinetic energy of the proton will increase. If the kinetic energy is increasing, the potential energy is decreasing. And if the potential energy decreases, we can see that the change is going to be negative, which is what we have here. Now let's move on to part C. Calculate the speed of the proton after moving through a displacement of 0.4 meters starting from rest. So how can we do this? Well, first, let's make more space. So the work that is done by the electric field on a proton as it moves from A to B, this is going to be equal to the negative change in potential energy. But I don't think we need to use that formula. I want to use this version. And that's also equal to negative Q delta V. So remember, the change in potential energy is equal to Q delta V. So this is still equal to negative delta U. They're all equal to each other. But I want to focus on this part of the equation. Now, work is equal to the change in kinetic energy. So we can replace W with KE final minus KE initial. Now, the proton is accelerating from rest. Therefore, the initial kinetic energy is going to be 0. So we have the final kinetic energy, which is 1/2 mv final squared, and that's equal to negative Q delta V. So don't confuse these two V's. This is the speed and this is the voltage, or the change in electric potential. So let's isolate V final. So I'm going to multiply both sides by 2, and I'm going to divide both sides by m. So on the left, the 2's are going to cancel, and the m is going to cancel. So I'm going to have V final squared is equal to negative 2Q delta V over m. And then let's take the square root of both sides. So the final speed, when accelerating from rest, if there's an initial speed, you need to take that into account here. But the final speed accelerating from rest is going to be the square root of negative 2 times the charge times the change in electric potential, or the voltage, divided by the mass. Now let's go ahead and plug in everything. So it's going to be negative 2 times the charge of a proton, which is positive 1.602 times 10 to the negative 19 coulombs. And then the change in voltage is negative 200 volts. I keep saying change in voltage. I mean, this is voltage, or change in electric potential. So if I mix it up, I mean the change in electric potential. So just keep that in mind. Now the mass of a proton, this you could look it up in your textbook. It's 1.67 times 10 to the negative 27 kilograms. Now the final speed has to be positive. So these two negative signs, they're going to cancel, giving us a positive result. So the value that I got for this problem is 195,886 meters per second. So we could say that's approximately, let me use the approximately symbol, 1.96 times 10 to the 5th power meters per second. We could move the decimal 5 units to the left to put it in scientific notation. So that's the final speed of the proton after moving through a displacement of 0.4 meters. Number 5. A uniform electric field with a magnitude of 800 newtons per coulomb is directed north. A negative 300 microcoulomb charge moves south by a distance of 30 centimeters. Part A. How much work is done by the electric field? So let's draw a picture. So we have an electric field that is directed due north. And then we have a negative charge that is moving due south. And we know the distance by which it moves. How much work is done by the electric field? Well, we know that work is equal to force times displacement. And force, the electric force exerted by an electric field on a charge, that force is equal to E times Q. So we can replace F with E times Q. So we get the work done by the electric field is equal to the electric field times the charge times the displacement of the charged particle. So in this example, the electric field has a magnitude of 800 newtons per coulomb. Now, is this value positive or negative? Well, the electric field is going in a positive y direction, so we're going to say this is positive 800. And then we have a negative charge, so this is going to be negative 300 times 10 to the negative 6 coulombs. And D is the displacement. The charge is moving 30 centimeters south. So the displacement, because it's going in the negative y direction, is going to be negative 0.30 meters. We need to divide this by 100 to convert that to meters. So let's calculate the work. So the work done in this example is positive 0.072 joules. And it makes sense why this answer would be positive. The negative charge is going to feel a force that will accelerate it in the opposite direction to the electric field. So because the electric field is directed north, the negative charge is going to feel a force that's going to direct it south. The work done by the electric field is positive because the electric force and the displacement vector are in the same direction. Now let's move on to part B. How much work is done by the electric field if the charge moved north by a distance of 50 centimeters due to its initial velocity? So let's draw a new picture. So the electric field is still directed north, But this time, the negative charge is initially moving north. It has an initial velocity, so its displacement, at least for a short period of time, is going to be north. Now, the electric force acting on the negative charge is still opposite to the direction of the electric field. So let's calculate the work done. Now, would the work be positive or negative in this case? Because the force vector and the displacement vector are opposite, we should get a negative sign for work. The work done by the electric force is going to be negative. Notice that the electric force is not accelerating the negative charge, it's slowing it down. The negative charge is initially moving up, the electric force is downward, so eventually the negative charge is going to slow down to a stop, it's going to go up, and then eventually it's going to come back down. But while it's going up, the electric force is doing negative work on the negative charge because it's slowing it down. It's decreasing its kinetic energy. So now let's use that other formula that we just got to calculate the work done. So the electric field is still going to be positive 800. It's still directed north. Q is the same, negative 300 microcoulombs. The only thing that's different is the displacement. It's now in the positive y direction. So we're traveling a distance of 50 centimeters north. So the displacement is going to be positive 0.5 meters, since we're moving in the positive y direction. And the answer that we get is indeed a negative answer. The work done by the electric field is going to be negative 0.12 joules. And so this is the answer. Number 6. An electric field of 500 newtons per coulomb is directed along the positive x-axis. How much work is done by the electric field on a 50 microcoulomb charge as it moves north by a distance of 40 centimeters? So let's draw a picture. So we have an electric field directed east along the positive x-axis, and we have a positive charge that has a displacement in the northward direction. How much work is done by the electric field on the charge? So we need to look at the force and displacement vectors. When the force and displacement vector are in the same direction, the work done by that force is positive. If these vectors are in opposite direction, the work done is negative. But what happens when the displacement vector and the force vector are perpendicular? In this case, no work is done. Here, the displacement vector is north. The positive charge will feel a force that will accelerate it in the direction of the electric field. Now, in this problem, this particular charge does not move east or west. Based on the question, it only moved north. We don't know the circumstances that caused this charge to move north. All we know is that it did. So if the force is trying to push it east, but it's not moving east, it's going north for whatever reason, this force has done no work on that charge because these two are perpendicular. So that's the answer for this problem. The work done is 0. Now let's work on this example. An electric field has a magnitude of 600 newtons per coulomb and is directed north. A 500 microcoulomb charge moves a distance of 8 meters at an angle of 330 degrees counterclockwise from the x-axis. How much work is done by the electric force on this charge during its 8-meter displacement? So let's draw what we know. So there's an electric field directed due north, and we have a positive charge. Let me draw the positive charge separately. Let's place it here. Now this positive charge is moving at an angle at 330 degrees. So we know this is 0, 90, 180, 270. So 330 is over here. If this is 330, then that creates a 30-degree reference angle. So the charge is moving in that direction. So if this is the displacement, this is the horizontal displacement, this is the vertical displacement. Now we know that the work done is going to be force times displacement. And we can replace force with the electric field times the charge times displacement. But recall, if the force and displacement vectors are perpendicular, the work done is 0. Now notice that the electric field is perpendicular to the horizontal displacement. So the electric field will do no work on a charge as it moves to the right. But now it's anti-parallel to the vertical displacement. So it will do work on the charge for this portion of the displacement of the charged particle. Now notice that the direction of E and dy, they're opposite. Because they're opposite, the work done is going to be negative. So the work done is dependent only on the part that is parallel to the electric field. So this becomes dy as opposed to d. Now we can calculate dy from d using SOHCAHTOA trigonometry. The y component is going to be d times sine theta. Now we can use 30 degrees as theta, or we could use 330. Sine 330 will give us a negative answer. Sine 30 will give us a positive answer. So regardless of which angle you choose to use, we just need to know that dy is going to be negative because it's moving in the negative direction. So to make this work, you can say you could use sine 330 or negative sine 30. We just need dy to be negative. So the electric field is positive 600. It's going in the positive y direction. So that's E. Q is positive 500. That's positive 500 microcoulombs. And then dy. So let's extend this equation. dy is going to be d sine theta. So this is the formula we're going to use to calculate the work since we're given an angle. So d is 8 meters, that's the displacement. And I'm going to use sine 330 relative to the positive x-axis because this is going to give us the negative value that we're looking for. So it's 600 times 500 times 10 to the negative 6. Sine 330 is negative 1/2 times 8, that's negative 4. So we can see that dy is negative, therefore w, the work done, is going to be negative. So the final answer is going to be negative 1.2 joules. So that's how much work is done by the electric field, or you could say by the electric force, which is due to the electric field. That's how much work is done by that force on this particular charge. Number 7, what is the change in electric potential energy of an electron that passes through a potential difference of 800 volts? And we want to calculate the answer in electron volts. 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. The formula that we need to use is this equation. The change in electric potential energy is going to be equal to the charge times the change in electric potential. The charge of 1 electron is, we can write it as 1e, but it has a negative charge. and it's passing through a potential difference of 800 volts. So this is positive 800. So the answer is simply negative 800 electron volts. Now, for those of you who may seem a little confused about that, here's another way in which you can get the answer. So let's use the same formula. And let's use the charge of an electron. One electron has a charge of negative 1.602 times 10 to the negative 19 coulombs. And the potential difference is 800. That's the voltage. But we can replace the unit volts with joules per coulomb. 1 volt is 1 joule per 1 coulomb. So here we can see the unit coulombs will cancel, giving us the energy, or the change in energy, in joules. So the change in electric potential energy is negative 1.2816 times 10 to the negative 16 joules. Now, electron volt is not a measure of voltage or electric potential. The electron volt is a measure of electric potential energy. It's a unit of energy and not a unit of voltage or electric potential. So don't get confused by that. Now let's use this conversion factor to convert from joules to electron volts. So we have 1 electron volt on top, 1.602 times 10 to the negative 19 joules. So now we can cross out the unit joules. If we divide these two numbers, we basically did one full circle, and we're going to get negative 800 electron volts. The first method was a lot easier, but nevertheless, you still get the same answer. So the electron volt is basically a unit of energy. You could use it to calculate electric potential energy. You can have kinetic energy in units of joules or electron volts. It's simply a unit of energy. And this is the conversion between the two. So you may want to write that down if you haven't done so already. Number 8. Which of the following expressions is correct regarding the electric potential of the points shown below? So is it going to be A, B, C, or D? Now we have the direction of the electric field. It's going east. The electric field tells us the direction in which the electric potential is changing. The electric field always points from a region of high potential to a region of low potential. So anywhere along this vertical line, the potential is the same. Let's say it's 300 volts. Anywhere along this particular vertical line, the potential will be the same, but it's going to be lower than 300. As we follow the electric field, the potential is decreasing from high to low. So this may be 200. And as we move further to the right, the potential is decreasing. So anywhere along that vertical line, it would be less, maybe 100. We don't know what the exact values are. But what we do know is that VA has a higher potential than VB. Now, points B and D are on the same line. So we can say that VB is equal to VD. They have the same potential. Now, B is greater than C. So both VB and VD, they're bigger than VC. But C and E are equal because they're at the same vertical line with the electric field. So we can say VC is equal to VE. Thus, the correct answer for this problem is answer choice C. VC is bigger than VB, but B and D are equal, which is greater than the potential at C, which is equal to E. But now let's say if you had a question like this. Let's say if there was a positive point charge at the center. And let's draw some circles around it. Now my circles aren't perfect, but let's assume that each circle is a perfect circle. Let me draw this better. I may need to take art class one day. So consider these points. Let's call this point A, B, C, D, and E. So rank the electric potential relative to the positive charge of each of these points. So remember, the electric potential generated by a point charge is V is equal to KQ over R, where R is the distance between the point charge and the point of interest. So as R increases, the electric potential decreases. As you move away from the charge, the potential decreases. Now what we have here is something called equipotential lines. Anywhere along the first circle, the potential is the same. So for that, it might be positive 300 for the first circle. For the second circle, anywhere along there, it might be positive 200. And the potential on the last circle might be positive 100. As you move away from the central positive charge, the electric potential decreases. So the potential at A is at the highest for the points listed, but A is equal to C because they're on the same equipotential line. The distance between point A and the charge is the same as the distance between point C and the charge. So the potential at A and the potential at C are the same, but it's bigger than the potential at B. Now B and D are on the same circle, so they have the same potential. VB is equal to VD. But B is bigger than E because E is further away. So E is going to have the lowest potential with respect to the positive charge. So that's it. That's how you can rank the electric potential given a situation like this. Number 9. A 400 microcoulomb charge is 5 millimeters away from a negative 300 microcoulomb charge. What is the electric potential energy of these two charges? So what formula do we need? Here's a simple way to remember the formula that you need for this equation or for this particular problem. So let's say we have the 400 microcoulomb charge here. At a distance 5 millimeters away, that charge, which we'll call Q1, will create an electric potential at this point, V1. The electric potential created by a point charge is KQ over R. Now let's say if we were to place the negative charge at this point. How can we calculate the potential energy of that charge given the electric potential that's produced by Q1? We know the electric potential of a charge is going to be the charge times, the electric potential energy. Let me say this one more time. So the electric potential energy, U, by a charge, Q, is going to be Q times the electric potential at that point. And the electric potential was created by charge 1. So this other Q, I guess we can call it charge 2. Now what I'm going to do is I'm going to replace V1 with what we have here. So this will help us to get the equation for the potential energy of two charges. It's K Q1 Q2 over R. So I like to combine these two equations because it helps me to remember what the equation is for the potential energy of two charges. Now granted, the way to really get this formula is to use calculus, but that's going to be beyond the scope of this course, or beyond the scope of this particular video. But that's the formula you need to calculate the potential energy in this problem. So now let's get the answer. I'm going to rewrite the formula here because I'm going to need more space. And so let me get rid of this. The electric potential energy between these two charges is going to be K, which is 9 times 10 to the 9, and then times Q1, which is 400 microcoulombs. Now we do need to plug in the sign, so this is going to be positive 400 times 10 to the negative 6 coulombs. And then Q2, we're going to plug in the sign. This is going to be negative 300 microcoulombs. So the electric potential energy can be positive or negative. So if you have two charges with opposite signs next to each other, the electric potential energy will be negative. If you have two charges with the same sign, be it both positive or both negative, then the electric potential energy of that system will be positive. And then we have R. R is 5 millimeters, or 0.05 meters. So now let's go ahead and plug everything in. So the answer that I got is negative 216,000 joules. So that is the electric potential energy of this system. Consider these two positive charges that are next to each other. Both of them will feel an electric force that will push them apart. Q1 is going to emit an electric field towards the right, and Q2 is going to feel a force that will be in the same direction as that electric field. Q2 also exerts an electric field on Q1, where Q1 will feel a force that will accelerate it in that direction from that electric field. And so they both exert forces on each other. But here's a question for you. We know that these two charges, they're going to move apart. What can you say about the work done by the electric force as they move apart? We know the work done is going to be positive because the force and the displacement vector are in the same direction. Now, what about the potential energy? Is it going to be increasing or decreasing? Well, we know that the potential energy between these two charges is K Q1 Q2 over R. R is the distance between the two charges. So as charge 2 moves away from charge 1, R increases, which means the potential energy decreases since R is on the bottom. They're inversely related. So as Q2 moves away from Q1, the potential energy decreases, which means that the change in potential energy is negative. So notice the difference between these two signs. They're opposite. So when dealing with the electric force, which is generated by the electric field, the work done by the electric force is negative delta U. In order for this to work, we need the negative sign. And we know that delta U is going to be the charge times the electric potential difference. So we get this equation. The work done by the electric force on a charge is negative Q delta V. Now the electric force is a conservative force, which means that energy will be conserved when the electric force is acting on these charges. The total mechanical energy of the system will remain constant. So that means that as the potential energy decreases, the kinetic energy will increase. So we can say that the change in kinetic energy is equal to the negative change in potential energy. Now, let's say if we apply an external force that is greater than the electric force with the goal of bringing the two charges closer together. We know the two charges, because they're like charges, they repel each other, they want to move apart. The electric force is pushing them apart. So it's going to take work to bring them closer together. So if we apply a very strong external force to bring the two charges together, how can we calculate the work done by that external force? Now, this external force is not a conservative force. The electric force, the gravitational force, those are conservative forces. The reason why they're conservative is because they keep the mechanical energy of the system the same. But when you apply an external force, you're actually giving the system additional energy. You put an energy into the system. You're increasing the total energy of the system. So as we apply this external force, the mechanical energy of the system will not be constant. It's going to change. So this no longer holds true when we apply an external force. So let's get rid of that, and let's get rid of this. Now, if the external force is greater than the electric force, the displacement vector is going to change. These two charges are going to move closer to each other. So now, if we focus on the work done by the electric field, it's no longer positive. The work done by the electric field is now going to be negative, because this electric field is trying to slow Q2 from moving to the left. The electric field wants Q2 to move to the right, but if it's moving to the left, this electric field is slowing it down. So as Q2 moves to the left, it's doing negative work, as we can see by the opposite two vectors here. The force and the displacement vector are no longer in the same direction. By the way, this is the work done by the electric force, not the external force. Now, what happens to the potential energy? Well, in this case, as we bring the two positive charges closer together, R is going to decrease. The distance between the two positive charges decreases, and based on this formula, the potential energy of that system increases. So delta U is positive. So notice that these signs are opposite again. And remember, this is the work done by the electric force. So the work done by the electric force is always going to be opposite to the sign of the change in potential energy. So this formula here gives us the work done by the electric force. If the work done is positive, the change in potential energy is negative. If the work done is negative, the change in potential energy is positive. That's why we have this negative sign. Now let's focus our attention on the external force, because the situation is going to be different there. The external force and the displacement vector are in the same direction. Therefore, the external force is doing positive work on that charge. If the external force is significantly greater than the electric force, we could have a net acceleration to the left, which means the speed of the charges could be increasing depending on how big this is, which means we could see an increase in kinetic energy. And not only that though, as the external force brings the two positive charges closer together, the distance between the two charges is still decreasing, which means that the potential energy is increasing. So the change in potential energy is positive. As for the kinetic energy, it depends on how big the external force is, because it's possible that you could have an external force that is just big enough to move the charge at constant speed, in which case the kinetic energy will be constant. But if you use a very large external force, you can move the charge with increase in speed, thus increasing the kinetic energy. So it really depends on the relative sizes of those two forces. By either case, the potential energy is going up. The kinetic energy may go up depending on how big this is. But notice that the signs of these two are the same. Therefore, this particular equation won't work for the external force. We have to get rid of the negative sign. The only way it's going to work is if we use this equation. W is equal to Q, positive Q, delta V. So this equation tells us the work done by the electric force. And this equation tells us the work done by the external force. So make sure you see the difference. So for the external force, it's doing positive work. It can increase the kinetic energy, and it's increasing the potential energy at the same time by bringing those two charges closer. As we can see, when R goes down, the potential energy goes up. So the work done by the external force is positive Q delta V. The work done by the electric force is negative Q delta V. Now, since both the potential energy and the kinetic energy can go up, energy is not conserved here. The mechanical energy is not remaining constant. Since both of these are increasing, the mechanical energy, which is the sum of the kinetic energy and the potential energy, this is going up as well. So thus the external force is a non-conservative force. It doesn't keep the energy of the system constant because it's adding energy to the system. Now let's summarize what we just learned so far. The gravitational force and the electric force are conservative forces. They keep the total mechanical energy of the system constant, which means that as the potential energy increases, the kinetic energy decreases, and vice versa. The external force that we applied in this example is a non-conservative force. It doesn't conserve the total mechanical energy. If strong enough, it can increase both the potential and the kinetic energy. Now the next thing you need to keep in mind is the work done by the electric force is negative Q delta V. The work done by the external force in this example is positive Q delta V. So keep that in mind. Number 10. How much work is required by an external force to bring a positive 20 microcoulomb charge from a very large distance away to a point 40 centimeters from a 80 microcoulomb charge? So let's draw the 80 microcoulomb charge. Let's put that here. Now we have another charge that is very far away, and that is the 20 microcoulomb charge. So we're applying an external force to bring this charge closer to the other charge. So let's say this is position A, the initial position, and then after some point, after we apply that force, it's going to be at position B. Let's call this Q1, and this is Q2. So this is where Q2 was initially, and this is where it is now, after some time. How can we calculate the work required to move Q2 from point A to point B? Well, the work required is going to be, this is the work done by an external force. It's going to be positive Q delta V. And delta V, that's going to be the final potential minus the initial potential. We're going from A to B. So A is initial, B is final. It's going to be VB, the potential at B, minus the potential at A. Now let's distribute Q. So it's QVB minus QVA. What's VB? VB is the electric potential created by Q1 at point B. The electric potential created by a point charge is K Q over R. So let's call this Q1, and this is going to be Q2. Now this R, this is going to be the R at point B. So that's the distance between Q1 and Q2 when Q2 is at point B. So this is going to be RB. And then minus, so this evidently is Q2 because we're moving Q2 from point A to point B, or through a potential difference. So this is going to be Q2 and then times the electric potential generated by Q1 at point A. So that's K Q1 over the distance between Q1 and point A is RA. So now we know the value of K, we know the value of Q1 and Q2. But what about RB and RA? So notice what this equation and that equation tells you. K Q1 Q2 over R, that is the equation for electric potential energy between 2 point charges. So the work done is really the change in potential energy. It is the potential energy of the two charges at point B minus the potential energy between the two charges at point A. So that's what we're looking for here, the difference in the potential energies. Now, point A is very, very far away. When you see a question like that, it's basically telling you that point A is so far that R is infinity. When you have infinity in the denominator of a fraction, that fraction goes to 0. For instance, if you were to take 5 and divide it by a large number like 1,000, you would get 0.005, which is close to 0. So because RA is so far away, this part becomes 0. So whenever you have two positive charges that are very, very far apart, the potential energy between those two charges is 0. So PEA is 0. Therefore, the work required by an external force to bring this charge from a very long or very far distance away to point B is simply going to be the potential energy at B, which is K Q1 Q2 over RB. So all we have to do to get the answer is simply use the potential energy formula. We just have to realize that the electric potential energy between two charges that are very, very far apart is 0. So the work required is simply going to be the potential energy of the two charges when they're close to each other. So let's get rid of this and let's start over. So the work required by the external force is going to be the potential energy at point B, which is K Q1 Q2 over R. So K is 9 times 10 to the 9. Q1 is going to be 80 microcoulombs. Q2 is positive 20 microcoulombs. And the distance between them is going to be 40 centimeters at point B, or 0.4 meters. So the answer is 36 joules, and it's positive. So that's how much work is required by the external force to bring the positive charge to a distance of 40 centimeters from Q1. And we can see why the work is positive. The external force is directed west, and as we move Q2 from point A to point B, the displacement vector is also west. So because these two vectors are in the same direction, the work done by this external force will be positive. Number 11. A 300 microcoulomb charge is fixed at the origin. A 40 microcoulomb charge is released from rest 60 centimeters to the right of the 300 microcoulomb charge. What will be the final speed of the 40 microcoulomb charge when it is very far away from the first charge? So let's begin by drawing a picture. So here's the first charge. It's fixed to the origin. And initially here is the second charge. It's initially 60 centimeters or 0.60 meters from the first charge. Let's call the first charge Q1 and the second one Q2. So this one is held fixed to the origin, and this one is free to move. So after some time, it's going to move from position A to position B. So at position B, Q2 is very far away. When we say very far, we're assuming that the distance between Q2 at point B is infinity from point A. And we want to determine the final speed when Q2 is at point B. So we need to use kinetic energy. Now, are there any external forces being applied to Q2? The only force that is acting on Q2 is the electric force. Q1 is going to repel Q2. There is no external forces acting on Q2. Therefore, energy will be conserved. Since the total mechanical energy of the system remains constant, we can say that the negative change in electric potential energy will equal the positive change in kinetic energy. As the electric potential energy decreases when Q2 moves from point A to point B, the kinetic energy of Q2 will increase. So the change in potential energy is going to be the final potential energy at B, which we'll call PEB, or just UB, minus the initial potential energy at A. And that's going to equal the final kinetic energy at B minus the initial kinetic energy at A. Now, what is the potential energy at B? Recall that potential energy between 2 point charges is K Q1 Q2 over R. Now, as R goes to infinity, the potential energy goes to 0. So the potential energy between these two charges at that huge distance is going to be 0. So UB is 0. Then we have minus UA. Now the kinetic energy at B, that's going to be 1/2 mv final squared. At point B, this is going to be moving. We need to calculate how fast it's moving at that point. Now what about the kinetic energy at A? At point A, the charge was released from rest. So the speed was 0, therefore the kinetic energy at A is 0. So therefore we have two negative signs here. So that's positive UA is equal to KEB. So for this problem, the electric potential energy at A is equal to the kinetic energy at B. So all of the electric potential energy that was stored in a system when these two charges were close to each other, all of that has been converted to kinetic energy. So the potential energy at A is going to be K Q1 Q2 over R, and the kinetic energy at B is going to be 1/2 mv final squared. So now let's do some algebra. So we have K and then times Q1. Q2 is 40 microcoulombs. The distance between the two charges at point A is 0.60. And the one thing I forgot to give you is the mass. So that's my fault. Let's assume that the mass is 1 kilogram. This is the mass of charge B. So we're going to keep it simple and use a value of 1. 9 times 10 to the 9 times 300 times 10 to the negative 6 times 40 times 10 to the negative 6 divided by 0.6. That's 180. If we multiply both sides by 2, 180 times 2 is 360. So now we need to take the square root of both sides. The final speed of this 1 kilogram charge is going to be 18.97 meters per second. So that's how you can calculate the final speed of the charge when it is very far away. So this problem is very similar to the last one, but with one key difference. Feel free to try this problem if you want to. So we have a 500 microcoulomb charge that is fixed at the origin, just like before. And there's another charge next to it. Let's call this Q1 and Q2. So Q2 is at point A right now. we're given the mass of Q2. It's released from rest 50 centimeters from the first charge. Let's go ahead and convert that to meters. So 50 centimeters is going to be 0.5 meters. What will be the final speed of the 60 microcoulomb charge, or Q2, when it is 2 meters away from the first charge? So here's Q2, the 60 microcoulomb charge, and it's at point B. Now point B is 2 meters away from the first charge. So it's 1.5 meters away from point A. Our goal is to calculate the final speed when Q2 reaches point B. So let's go ahead and do that. Just like the last problem, the only force that's acted on Q2 that's accelerating it towards point B is the electric force, which is a conservative force. We don't have any external forces acting on these charges. So the total mechanical energy of the system will be conserved. So therefore, the negative change in potential energy will be equal to the positive change in kinetic energy. So the final potential at B minus the initial potential at A, of course with the negative sign in front, that's going to equal the kinetic energy at B minus the kinetic energy at A. So this is going to be, if we distribute the negative sign, it's going to be negative UB plus UA, but we could reverse that into this. We can write it as UA minus UB. Now the kinetic energy at A, that's 0, because at point A, the 60 microcoulomb charge was at rest. So it's going to be UA, the potential energy at A minus the potential energy at B, and that's going to equal the final kinetic energy at B. So the only difference between this problem and the last was that UB was 0. But this time, B is not at infinity. B is at a certain distance. So there is a potential at B. I mean specifically an electric potential energy at B. So let's calculate UA and UB. So UA is going to be K Q1 Q2 over RA. UB is going to be K Q1 Q2 over RB. And this is going to be 1/2 MV final squared. Now to simplify the math, we could factor out K Q1 Q2 because they're the same. If we take that out, this is going to be 1 over RA minus 1 over RB. So we have K 9 times 10 to the 9. Q1 is 500 microcoulombs. Q2 is 60 microcoulombs. RA, that's 0.5 meters, so this is 1 over 0.5. RB is going to be the sum of these two, or 2 meters. And that's going to be 1/2 times the mass of 4 kilograms times V final squared. And I need to make one small correction. That should be a -6, not a -9. Now let's plug in the numbers. 9 times 10 to the 9 times 500 times 10 to the -6, and then times 60 times 10 to the -6. These three numbers, when multiplied, that's going to be 270. 1 over 0.5 is 2, and 1 over 2 is 0.5. Half of 4 is 2. So 2 minus 0.5, that's 1.5 times 270. So this is 405, which is equal to 2 V final squared. So now let's divide both sides by 2. So we get 202.5 is equal to V final squared. And now we could take the square root of both sides. And thus the final speed of the 4 kilogram 60 microcoulomb charge at point B is going to be 14.2 meters per second. And that's it. So that's how you can solve this particular problem using conservation of energy. Number 13. 3-point charges with magnitudes 30 microcoulomb, 20 microcoulombs, and negative 10 microcoulombs form an equilateral triangle with a side length of 1 centimeter. What is the total electric potential energy of this system? So let's call this Q1, Q2, and Q3. So the total electric potential energy is going to be the sum of the electric potential energy between charges 1 and 2 plus the potential energy between charges 1 and 3, and then plus the electric potential energy between charges 2 and 3. So we need to calculate each one. So let me just erase this. Let's do it one at a time. So let's start with the potential energy between 1 and 2. So it's going to be K, and then Q1. Q1 is 30 microcoulombs times Q2, which is 20 microcoulombs. And the distance is 1 centimeter. And since we have an equilateral triangle, that's going to be the same for all 3 sides. 1 centimeter is 0.01 meters. So you should get positive 540 joules for the electric potential energy between charges 1 and 2. Now let's do the same for finding the electric potential energy between charges 1 and 3. So we have K and then Q1. So that's positive 30 times 10 to negative 6. Q3 rather, that's going to be negative. So we need to incorporate the negative sign to get this right. The electric potential energy can be negative, so keep that in mind. So for the potential energy between charges 1 and 3, you should get negative 270 joules. Now let's do the same between these 2 charges. So we're going to find the potential energy between charges 2 and 3. So it's going to be 20 microcoulombs instead of 30. And then we're going to have negative 10 again. So this is going to be negative 180 joules. So now we can calculate the total electric potential energy of the system by adding these numbers. So it's going to be positive 540 and then minus 270, or plus negative 270 if you want to do it that way, and then minus 180. So the total potential energy of these 3 charges is going to be positive 90 joules. So that's the answer for part A. That's how you can find the total electric potential energy of the system. Now let's move on to part B. How much work is required by an external force to bring these three charges into this configuration if they were initially very far apart from each other? So how can we find the answer? When dealing with an external force bringing these charges, we know that W can be equal to positive Q delta V. And the change in potential energy is Q delta V. So W is going to equal positive delta U for this example, which is UB minus UA. Now we have the potential energy at B. That's the final potential energy when the charges have been assembled together. UA is the potential energy of the system initially. That is when the charges are very, very far apart. And we know that U is equal to K, Q1, Q2 of R. Whenever R goes to infinity, the electric potential goes to zero. So when the charges are very, very far apart, the potential energy is zero. So we can say that UA is approximately zero. So if UA is zero, then the work done, or the work that's required by an external force to bring these three charges together from a very, very far distance, if they were initially very far apart, then the work becomes equal to simply UB. So the answer is simply 90 joules. 90 joules of work is required for an external force to bring these three charges together if they're initially very far apart from each other. So that's it for part B.